So, hello everyone. Today I'd like to show you a quick introduction how to solve partial differential equations of second order. And for that, I'd like to give you a general example what that might look like. So, if we have certain partial equation of the second order, we have some coefficients and the second derivatives of a function u. So I'm only saying that u is a function of x and y to not make it too complicated. So as you might see, we have those coefficients, which are functions from x, y. This one as well. And all the rest on the right side, we can actually name it. We can actually go on with the coefficients for the first derivations, and which could be plus any other stuff or any other function. But if you name all of this just first order stuff, will make it easier, because that's the important thing. So I can easily go on with that. AUXX plus BUXY, so these are the second derivatives, and CYY equals first order stuff. Let me name it like that. And yeah, so UXX means, just to clarify, yes, and so on. So if you look at this equation, how are we able to solve that easily? So first of all, you might use a separation approach with a function called, with splitting up the searched function in XX and a function of YY. But we're not going to start with that approach, because this one gives us, how can I say, interfering solutions, especially for wave equations. And yeah, we don't want to have this type of solution at the beginning, because I want to show you another method which gives you the non-interferical solutions, which is the characteristic method, which you might have heard of in my first videos, or which you might saw anywhere else, which gives you the non-interference solutions. That means we get the characteristic solutions, and what that is, I can show you actually. Let me go back to chapter 2. So no, let me go back to chapter 1. So a characteristic of solutions will look at a certain solution. Let's name that, could be ZXY or UXY, it doesn't matter how you name it. This could also be, it's not important how you name it, but if you look at a certain curve, so what you do is looking at a certain curve and then looking at all the solution of the searched function on that curve. So you're kind of reducing the dimension to first order problems. So despite solving the partial differential equation in the whole field, you're only solving these one-dimensional equations, because if you say that all our solution on the xy curve, so let's name that a curve gamma, which depends on xy, and its parameterization is given by a parameter s. That's why I named that s. If you look at all the solution on that curve, you're only getting another curve in our solution space. So our solution space is given by uxy, by the searched function, but you kind of just starting to solve it on a one-dimensional curve, which gives you a one-dimensional solution in the 3D plane. So here you have a curve in the xy plane, but now you have a curve which is a solution in the three-dimensional plane. And if you want to get the whole solution space, which is not a curve but a plane, as I mentioned, you have to kind of expand these curved solutions. Follow that. You have to expand this solution by tiny different initial conditions, or you will get constant solutions, and then you have to expand it, and that will give you the whole solution. But that sounds a bit complicated when just talking about it. It is easier to see that in the first order partial differential equation. So for the second order, it's actually uses the characteristic method, but it's not going to be that complicated, because what I want to do, or I want to show you in this example, is actually how you can solve these equations by reducing it to a canonical form. So that's the second order. I can afterwards show you through the connection to first order problems, partial differential equations, with the characteristic method. But if you want to solve those second orders, you're going to use the characteristic method and then transform it, or transform it to its canonical form, or reduce it to that, which means you want to have a solution. So you're searching new coordinates which depend from xy, so you're searching new coordinates eta and xi, or let us name it xi and eta, because it's the alphabet, row of the alphabet. So you're searching those coordinates, which are functions actually. So you got xy, so this is a kind of function of xy, as well as this one. And then if you're able to find these functions or these relations, you'll be able to easily reduce the system. It's a bit complicated at the beginning, but I'm gonna explain you step by step. Hope that you get it, because it's still not easy in the beginning, but I think you will be able to understand soon. So what can we do to figure out those relations? So first of all, if you look at our general equation, we have coefficients which are functions, and these coefficients, they don't always have to be functions or complicated functions, but if we look at these coefficients, these will define us how these functions or these coordinates will look. And if we have those coordinates, the derivatives will also look different in terms of x and y. So if you want to have dx in terms of, so that's the differential operator d to dx, and if you want to have if you want to know how this looks in the other coordinate system, you will just apply the chain rule. So that means dx will be d of anything derived by d eta, or let's start with xi, dxi xi, and then the derivative of xi in terms of x plus, because it depends on both, d eta and the eta derived by dx as well. The same for dy. I'm just gonna shorten it a bit, like this we can call d xi, and then instead of taking the derivative of x, we take the derivative of y, so which gives us xi y, plus, not to forget, same on the right side. So yeah, hope you get the notation. This one means xi y and eta y, or eta x and xi x, first derivative. Okay, and then if you go on with the xx, will look more complicated, but it's just the chain rule again. So if we go on with the chain rule and take the derivative of this term here above, we'll have dx of d xi plus xi x plus xi eta, and if you take this derivative, it will give us a term, like we take this one and apply the chain rule to this term, then we apply the chain rule to this term, and then we sum it up, which you can try out by yourself, which will give you first of all second derivative of this times this squared plus first derivative of this. So that's just the basic chain rule, but we don't have to forget the dependence of eta. So you get xi eta times xi eta x, and then you might think we're ready, or we've done, but not yet, because I have to do the same with on the right side with the right term. So that will give us the eta, or let me put that here because we need the space. So we get eta plus eta x squared plus d eta times eta xx, and the derivative of this one, or this term as well in terms of x, so which will give us the same as we have here, but because the order of derivative is not important, so if we take the derivative of xi and eta, or eta and xi, it will be the same. So we can just add another 2, and then we will have, let me make that clear, and then we will have our derivative, actually our second derivative. The same counts for the yy. just need to change the x's with y, and then we will have our derivatives. So the right way might look a little bit messy now, but it will get clearer. So why? Alright. Why do I do that? Because we want to plug in, because for the moment we don't know what our eta and psi will be, but I'm just going to do it generally, so that will give you the derivation of our f and g functions, or that will define our functions actually. Why is that? Because if you look at our general equation in this form, and I told you a, b, and c are x's, and if we want to like reduce it to a canonical form, that will mean we only want to have b left and a and c vanish. But how can we do that, or why is that? It is you will see it soon. So actually we want to have a kind of equation which gives us, let me put that in color. The canonical form will be b x y equals first order stuff, or another first order stuff, because it doesn't matter if we divide by b. And this term we can easily integrate on the left side, 2 times dx dy, and excuse me, it actually has to be psi eta here as well. And after that we will get our solution by solving the right integration term, and then easily plug in the functions, or like the relations between these new coordinates and our old coordinates. Then we will get the general solution. This might not always work for every function, but it will work for certain problems, for certain given problems. If you got to be asked for a problem solved by the characteristic method, you're gonna use that if it's second order, first order. So yeah. Okay, let's go back to this derivation stuff. So here I just made a copy of these functions. So what you can see here is, that's the general equation again. And if you plug in those derivations, it will look a bit complicated. So what we are going to do now, let me clear that up, maybe write it a bit clearer. What we're going to do now is we have our function xx, okay, plus buxy plus cuy equals first order stuff. We are now going to plug in those derivations, which will give us a new function in terms of, so this might look a bit messy if I plug in all in that line. That won't be enough space for plugging in all of those derivations. But if you understand what I mean, we want to have a new kind of equation with any new coefficients. Let me call that a plus B always empty order, but yeah, and eta equals first order stuff, and we want those to, we will see now, because of symmetry of these two operators here, that the new coefficients A with the bar over there and C with the bar over there, or A hat and C hat, will be the same because of the symmetry of those two like derivations, or yeah, of our new coordinates. And that means they will be the same, and if we cancel out one of this or this, we'll have to solve characteristic equations. That's why it's called characteristic method. But yeah, so I'm gonna show you the derivation. If you plug in these coefficients, so what I've done is, okay, this is from another lecture, so you can easy, or actually you have to know that if you introducing new coordinates and you have a function u eta or xc, so let's just assume if you have u xy is also the same as c eta, because we're just giving it a new name because it's not the same function anymore, because it's referring to other coordinates, but it will be the same. So don't get confused by the set function, which could also, you could also name it u, but it's not mathematically rigorous to do it like that. It's easier to understand, but yeah, just to be sure, this that will be the equal to u, to the search function. So if you plug in all those derivations, I'm gonna go through that because you can do it by yourself. Actually, you will have all these terms, what we have here. You see here, you got function. You have to plug in a function to that operator. That's for sure, because you can see you should plug in a function if you use a function, if you use this operator, and that will be z xi, and all the stuff which relates to the derivation operator. Same for, so we got a as a coefficient, we got let me see, that should be b actually, so we got b depending from, b was dependent from x and y. Now it's dependent from y, xi and eta, but it's not actually important. It's just important to set all those operators in the right order. So after having all this, I will give you I will show you what sorting will give you. So you have to sort all these derivations in terms of the coefficients. So you want all those xi derivations on one side, all those eta, and all those xi eta derivations on one side, like here. And if you've done that, that will give you the actual form, the normal form, which will lead you to the characteristical equations, which you need to solve in order to cancel out these coefficients here, the a hat and c hat, in order to get the canonical form. And as I mentioned, it might not work all the time, but it will work if you have a given question to solve a second order partial differential equation by the old method of characteristic. So that's the main approach. So let me quickly give you the next step.